So it's time to review some applications of derivatives. So first we're going to look at some curve sketching. So we've got a function here, and we want to find the critical points, the extrema, increasing, decreasing, all that good stuff. So we need derivatives. So let's find the derivatives. We got f prime of x. That's going to be 1x squared plus 2x minus 8. And to find critical values, we set that equal to 0. So 0 equals x squared plus 2x minus 8. This should be able to be factored. You can kind of expect that with AP stuff. You might need the quadratic formula, but factor. This is a no calculator test here, by the way. So I think that works. That looks pretty good. And so we get solutions of x equals -4 and x equals 2. What makes this 0? What makes this 0? Okay, so our critical points are going to be x equals -4 and 2. Okay, the extremas now, we can go ahead and we can make a number line here. So let's get a number line going on here. And so at -4 and at 2. This is f prime. Make sure you label your number lines. We're going to plug in and test values with the derivative. Now, you might want to test it in with this factored form here. So if we plug in -5 into this factored form, we're going to get a -5 will give you a negative number here and a negative number. Negative times negative is a positive. So this is positive. Plug in maybe 0 is in here. 0, when you get 0 plus 4 is positive. 0 minus 2 is negative. Positive times negative is a negative. Then we plug in 3. We get 7 and 1. So positive and positive. Okay, we don't actually need to figure out what the numbers are. I know I just said 7 and 1. But the moral of the story is just need to know what we're multiplying. Are we multiplying positive numbers or negative numbers? Okay, this is the first derivative, so that tells us this is increasing, decreasing, and increasing. Okay, so that means we have the extremas. We got a max at -4, and we have a min at 2. We're not trying to find the y values right now, just where they happen. All right. The intervals of increasing, well, we can use that our number line there, -infinity to -4, and from 2 to infinity. Decreasing is right in the middle of those, -4 to 2. So we got decreasing when the first derivative is negative. Now we want inflection points, so we're going to need the second derivative here. So let's go find the second derivative, looking back up top to the expanded version there. So we get f double prime of x is 2x plus 2, using the power rule here. And we want to set that equal to 0. 2x plus 2, that's going to be x is -1. So we get an inflection point, or a possible inflection point here at -1. We should test it out. So f double prime. So -1 is the possible inflection value. Plug in a negative number like -2. And when you plug in -2, we get -4 plus 2. That's a negative number. When we plug in +2 or 0, even when you plug in 0, you get a positive number here. So concavity does change. Now keep in mind, this is what we expect. This is concave down, concave up. We know what a cubic function looks like, so we should totally expect this. We know that the cubic function is going to look something like this curve here. Okay, and it's got a positive leading coefficient. So don't forget that we know what a cubic function looks like. Okay. So our inflection points do happen at x equals -1 because concavity changes. Concave up is from -1 to infinity. Concave down is from -infinity to -1. Okay? There you have it. Well, let's try a rational function. Now, this turns out to be a pretty challenging one, all right? So this will pull out all the stops. So we're going to need our calculator at some point here. So when we get to inflection points and the second derivative, okay, go to your calculator, okay? Second derivative, use the calculator. Use a calculator to solve. And everything from kind of here on down. Now you might say, well, we can just use a calculator to graph it. Yeah, that's true. But we're going to find all these important points using what we know about derivatives, okay? So we'll use the calculator from there on. And when you do that using your TI Inspire, what I'd recommend you do is enter f of x colon equals 2x minus 4, and then call g of x equal to the derivative of f of x. That'll be the first derivative. And then let f of x, and no, let's pick a different letter, h of x, b colon equals, store equals, the derivative of g of x. That'll be your second derivative. All right. So if you just do this right off the bat, then when you start using your calculator, then you don't have to retype anymore. You just have your derivatives, and you can find your important points. Okay. All right. Well, let's go ahead and dive into it and see how far we can get without our calculator, and then it's going to get really ugly, and we'll go from there. So we've got a rational function here, 2x minus 4 over x squared minus 1. We're going to need a derivative here. So let's go ahead and find our derivative. F prime of x. We're going to need quotient rule. Derivative of the top times the bottom minus the top. Don't forget your parentheses here. Times the derivative of the bottom. Derivative of the bottom is just 2x. You don't need parentheses there, of course. Divided by x squared minus 1. Now, if we need to clean this up here. If we could factor it, that'd be good. We could factor out a 2. That's not really going to do much for us there. If we had a parentheses that was a common factor, we could do that. Again, this is, if we pull out a 2, this is 2x minus 2. That's not a common factor there. So, nope, not much is gonna help us there. All right. So let's just go ahead and clean up that top. Okay, we can distribute out that 2x squared minus 2. Now be careful here. We're going to distribute this 2x there. We also need to distribute this negative, so it's going to change the sign. Okay, so if you want to do this in 2 steps, it's not a bad idea. So we're going to have negative 2x times 2x. That's going to be a negative 4x squared. We got this negative times negative 4, which is positive 4. Positive 4 times 2x is positive 8x. Okay. All right. I think that looks pretty good. You know what? I forgot to square the bottom. Did you catch that? Maybe I said it and didn't write it. I don't know. Quotient rule says we got to square the bottom, right? All right, we don't need to do much with this. Okay, we're going to, in just a second, we're going to ask ourselves when this is 0, so it doesn't do any good to multiply this out. Okay, we're going to be looking for when this is 0 too, so we do need to kind of multiply this out. So, all right, or clean it up like we are. So we end up with negative 2x squared plus 8x minus 2. Okay, and x squared minus 1. Maybe we will go ahead and pull that. Let's pull a negative 2 out there. Negative 2, x squared minus 4x minus 1, plus 1. Why would we do that? Well, then I can more easily see if this factors. Does it factor? It actually looks like it doesn't. Two numbers that add the negative 4 and multiply to 1. Yeah, they don't exist. So, all right, we're going to have to use a quadratic formula there in a second. So we're going to need to find our critical values. So our critical values happen when this is 0 or when it's undefined. So we set this equal to 0. It's when the top is 0. What makes the top 0? Well, that's negative 2 times x squared minus 4x plus 1. And if we just divide off that negative 2 from both sides, okay, you can divide this side by negative 2, divide this side by negative 2. It just goes away because of the 0 there. X squared minus 4x plus 1. Can't be factored, so let's use our quadratic formula. X equals negative b plus or minus square root b squared minus 4 times a times c all over 2 times negative 2a. b squared minus 4ac in the parentheses there. Watch out for these negatives. That'll get you. All right. So 4 plus or minus. And what do we got here? We got 16. 16 minus 4. That would be 12. Okay. And if we clean this up, this is 4 plus or minus, this is square root of 4 times square root of 3, so that's 2 square root of 3 all over 2, which is, divide them both by 2, divide both ways, 2 plus or minus the square root of 3. All right. So that makes the top 0, 2 plus or minus the square root of 3. What makes the bottom 0? Well, that's going to be plus or minus 1. Because what makes 0 equal to x squared minus 1? Well, that does factor into x plus 1 times x minus 1. And that means x is plus or minus 1. Okay, so we have some critical values at 1, negative 1, and at 2 plus the square root of 3, 2 minus the square root of 3. Okay? All right, a lot going on here. So running out of room probably. So let's make a number line for f prime. Now, by the way, the square root of 3 is about 1.7. Okay, so this is about, just to kind of give yourself an approximation, 2 minus the square root of 3 is about 2 minus 1.7. That's about 0.3. 2 plus 1.7 is about 3.7. Okay, so we've got negative 1. We've got 2 minus the square root of 3, which is about 0.3. So that's about 0.3. We'll put that in parentheses there. We've got positive 1. And we've got 2 plus the square root of 3. And that's about 3.7-ish. Okay. All right. So where's the critical values? Well, we had x equals plus or minus 1 and plus 2 plus or minus the square root of 3. Okay. All right. Well, where's the extrema? Let's find our values. All right. Plug in a negative 2. And we're going to plug it into f prime. So that's going to be, let's go with this one maybe here. Okay. So if we plug in like negative 2, all right, what are we going to get here? On the bottom, by the way, is always going to be positive. You notice that? Because it's going to be squared, all right? So if we plug in negative 2, all right, this is going to get a little ugly here. Negative 2 is going to give us 4 plus 8 plus 1. So that all is going to be positive when you plug in negative 2. Okay, so that's all positive down there, times a negative divided by a positive. This whole thing is going to be negative. If we plug in something like, this is like 0.3, so 0 is right in between here. If we plug in 0, the bottom's always positive. This will be 1 when you plug in 0. 1 times 2, negative 2, that'll be negative. So negative over positive gives us negative. plug in something between 0.3 and 1, all right? Now we're going to have to do like a half. A half is between that, all right? Bottom's always positive. Plug in a half, all right? And we got, this is positive 1/4 minus 2 plus 1. When you plug in a half, you get 1/4 minus 2 plus 1. That's a negative number. So negative number times a negative number is positive, and the bottom is always positive. One more. How about a number like positive 2? Bottom's always positive. Positive 2 would give us 4 minus 8 plus 1 when you plug in 2. So that means this is negative times a negative, which means the whole thing comes out to be positive over positive. Positive over positive is positive. All right, there you have it. So we're going down, down, up, up. Okay? All right, so there's all our information there. We do have an extrema. Looks like we got an extrema. Now, these are, by the way, these are asymptotes, because these are what makes the original one undefined. So the -1 and +1 are asymptote. Keep that in mind. And it looks like we have a minimum here. So extrema, we have a minimum at x equals 2 minus the square root of 3. And you know what? Actually, we need to check one more thing here. We need to check what's going on over here. We need to plug in a number to the right of this here. So let's plug in like 4. So 4, if you plug in 4 here, we get 16 minus 16 plus 1. So that would be 0 plus 1, which is a positive number. Positive number there times negative. We have negative on top. We got one more. It looks like this is negative. Okay, so this is going down to the right of that. Okay, so we have a maximum also. Look at that. We got a max at x equals 2 plus the square root of 3. All right, so let's get all our intervals here. So increasing, just reading our number line, we have from 2 minus the square root of 3 to 1. Okay, we have from 1 to 2 plus the square root of 3. Intervals of decreasing, we have from negative infinity to -1, from -1 to 2 minus the square root of 3, and from 2 plus the square root of 3 to infinity. All right, and last one, inflection point. That means we need to find the second derivative. Okay, well, if you got any room on your paper, let's go find the second derivative here. Which one should we use? Well, might go from this version. These are all simplified versions of the first derivative. Now, this is where it gets pretty ugly. So you can use your calculator here at this point, all right? So h of x, f double prime of x. You should be able to work it out, but it's a lot of tedious legwork. So we end up with something like this. Okay, plus 3x minus 2 all over 2x squared. Nope, sorry, just x squared minus 1 to the third. So this is going to be, let's try that again, x squared minus 1 to the third. All right, now we want to set that equal to 0. We want to find out when f double prime of x is equal to 0. So again, we can use our calculator for that, and we can find out at x equals 5.52233. Okay, so 5.522. All right, so our number line is going to look like this for f double prime, and we have at 5.5, got a possible inflection value. We do have possible inflection value at 1 and -1. Okay, those are asymptotes. All right, so we should check out our concavity change there. All right, so let's plug in some numbers here. All right, if we plug in 0, now we're going to plug them into here. Okay, if you have this in your calculator, which we probably did there, the best way to do this is if you enter this into a function like h of x or something like that. Type this in and then just plug in h of 0 and figure out what it is. Plug in h of 0.5. No, I'm sorry, 0 would be right in here, huh? So what happens is we get something like this. Again, using your calculator, plugging in values like -2 and 0 and 4 and 6 or something like that. Let your calculator do the work. You get negative, positive, negative, positive. That gives us our concavity. Our concavity is down, up, down, up. All right. So we have our inflection points. Now 1 and -1 are not inflection points because they're undefined in the original problem. So we have an inflection point at x equals 5.5. All right, and concave up happens from -1 to 1 and from 5.5 to infinity. Okay, a lot going on here. So now we weren't asked to sketch this, but kind of interesting here if we give it a try. So if we sketch this, we know it's a rational function. We know at -1 and 1, there's an asymptote. We know that there is a, let's see, we have a minimum at 2 minus the square root of 3, and this is like 2 minus 1.7, so this is about 0.3. So there's a minimum at 0.3. So there's some point when x is 0.3, y is I don't know. If I plug in 0.3 here, I get negative on top and negative on bottom. So I don't exactly know where it is, but I do know it's above. And that's a minimum. Now notice that between -1 and 1, the concavity is concave up. And notice that to the right of this point, 2 minus the square root of 3. All right, so let's put this down here. So this is 0.3, also known as about 2 minus the square root of 3. So to the right of that, we're going up, and to the left of that, we're going up. Okay, so it's not really symmetrical because it's going to these asymptotes, so it's kind of lopsided. So we know that much. All right. We know that at 5.5, there's a minimum. So 1, 2, 3, 4, 5, 6. Okay, so there's a minimum. Now 5.5, let's see what kind of number we get. Plug in 5.5. That's positive on top, positive on bottom. So there's some positive number. Okay, and that's going to be a minimum. Oh, I'm sorry, it's going to be a maximum. 5.5, that number there is a maximum, okay? Where did I get the 5.5? That's a change in inflection. Sorry about that. That's an inflection point. So we've got an inflection point there. We've got a maximum that happens at 2 plus the square root of 3. 2 plus the square root of 3 is that number. That's about 2 plus 1.7. That's about 4.7 actually. 4.7. So there's a maximum up here somewhere. Okay. And then there's an inflection point. Okay. We also know this. As x goes to infinity, this is going to, well, the bottom is squared. So as x goes to infinity, this goes to infinity squared. This is going to 0 because there's a bigger degree on bottom. So it's going to 0. And same thing as we go to negative infinity, it's going to 0. So the end behavior is that. All right? So, all right. So this, there it is. This is a maximum. And we know that's an asymptote. There it is. Something like that. Okay? We know to the left of -1, it is concave down. Concave down. And it is decreasing. Okay? And we know it goes So it's decreasing, it's going down, and we know it goes to infinity. So there's no maximum over here on the left, so we got something like this. It's going to 0, there's an asymptote at 0, and there's a blue asymptote. So anyways, something like that, a kind of crazy one there, all right? But again, that includes all of the stuff that's going on. Kind of some crazy derivatives, but we understand hopefully what to do with them. Second derivative gives us concavity. First derivative gives us increasing, decreasing. Great job if you hung with us through that. All right, let's look at some simpler ones next. So let's take a look at this graph that has no numbers in it, but we can still find out the important information. All right, so this is f of x. Keep that in mind. Okay, so we want to find the critical values. That's where we have horizontal asymptotes. That's going to happen at 0, at b, and at e. Where's the extremas? Well, the same place, right? 0b at e, right? We can't have a critical value when we have a horizontal tangent line. If we had a situation like this, right there, that would have a horizontal tangent line. That the tangent would be 0 for just a moment. All right, an interval of increasing. Well, again, we're just looking at f of x. So it's increasing from 0 to b, going up there, and then from e to infinity. Where is it decreasing? Well, from negative infinity to 0, and from b to e. Where are the inflection points? Well, that's where concavity changes. So this is concave up. So it looks like right here about a, there's an inflection point at x equals a. And there should be another one. It's probably here. It looks like it's here where this d is, all right? If you said c, you're on the right track, but I think it's more like d. All right, and that's it. Where is it concave up? Well, it changes at those inflection points. So we got negative infinity to a, and then it's concave up here from this point D to infinity. Where is it concave down? Well, that's from A to D, and that's it. Okay? So there's all the features just by looking at the graph of f of x. Now, let's look at another graph. Now, it looks the same, but it's f prime now. All right, so we might just kind of block that other graph out of our mind totally. We're talking about a different function here, all right? So we want to find critical points. Now, especially in this case, we want to keep in mind what we're looking for. Critical points happen when f prime equals 0. And where does that happen? Well, f prime is 0 at 0, and at c, and at f. Okay? Now, which one of those are extremas? Well, it might help to do a number line here. So let's do a number line here, and let's translate this for f prime. F prime is 0 at 0, at c, and at f. Okay? Now, what's happening? What's the sign of f prime to the left of 0? It's above the axis, so it's positive. From 0 to c, it's above, so it's positive. From c to f, it's below the axis, so it's negative. And from f to infinity, it's above, so that's positive. So extremas happen when we change increasing or decreasing. Okay, so we change the sign. So we're increasing, we're increasing, we're decreasing, we're increasing. So we have a max at c at x equals c, and we have a minimum at x equals f. Okay. Well, so where is it increasing and decreasing? Well, we get that from here. Now a number line is helpful because we just translate it to positive. So increasing means that we have f prime is greater than 0. It's positive, and that happens at negative infinity to 0, and from 0 to c, and from f to infinity. Where is it decreasing? Well, that happens when f prime is less than 0, and that is at from c to f. Now, where do we get inflection points? Inflection points happens when the second derivative equals 0. So the second derivative is 0 when, well, and remember, second derivative is the slope of the first derivative. Okay, so it's the slope of this graph. Okay, so where on this graph do we have a slope of 0 or a tangent line of 0? Well, that happens at the mins and maxes of this graph. Okay, so the possible inflection points, let's go into another little number line here. So the possible inflection points happen at 0, at B, and at E. Now if we check the slope, again we're looking at the slope of this graph. The slope of this graph is the second derivative, so the slope here is negative. The slope here is positive, then negative, then positive. So we're talking the slope of this graph. Okay, so we'll use that in a second to sketch a graph. All right, so where is it concave? Oh, inflection points is where concavity changes. Okay, so it changes at 0, B, and E. So that's at 0, B, and E. Where is it concave up? Well, that is when the second derivative is positive. It's concave down when it's negative. So that happens, let's see, the positive is from 0 to B and from E to infinity. Concave down happens from negative infinity to 0 and B to E. Okay? And last but not least, we want to sketch a graph using these key features, okay? So it helps that we kind of line these two number lines up, okay? And then we can say this. To the left of 0, we're increasing concave down. So it's going up, but concave down. Okay, now we don't know any values here. We might assume, usually we'll say something like this, assume f of 0 is 0. Okay, so we need kind of a starting point. So there's more than one answer because you could start it, you could have different x-intercepts. So this is going to be concave down and increasing. So it's increasing and concave down, something like that, okay? Then what happens there? Now after 0, it's still increasing and it's concave up. And that happens until B. So it's going to increase, concave up till B. Okay, now at B, I'm going to run out of room here. Where B, we're still increasing, but we start to be concave down until C, which C is a maximum. So something like that. All right, and then nothing happens at D, notice that. But E is our next point where the inflection changes. We're going down, decreasing, concave down, until we hit E. So we're decreasing concave down until E, wherever that is. And then we change to decreasing concave up until F. So F is a minimum. So we're scooping down. And then at F, we turn and we're concave up. And to be a little smoother than that, but that's the idea. So after F, we're concave up, increasing. Okay? So we have an inflection point at B. I kind of ran out of room, so we got a little bit of curve here, all right, and something like that. So switching gears from curve sketching, we got a little mean value theorem here. The mean value theorem, we need to determine if it's if it meets the hypotheses. The hypotheses are it has to be continuous and differentiable on the interval. Okay, differentiable. Okay, So first thing we've got to do is decide if the mean value theorem applies here. So we look here at this function. Is it continuous on this interval? It has a break at -3. Is -3 on this interval? It is. And so the answer would be to part I, no, it's not continuous at x equals -3. What about this one? Is it continuous from 2 to 4? Well, there's a break at 1, but 1 is not on this. There's an asymptote at 1. So 1 is not on this, so and it is going to be differentiable because it's a smooth curve. We know that about rational functions. So yes, okay, it's continuous and differentiable on 2, 4. How about this one? This is a cube root. Cube root is defined for all values. It doesn't have any domain restrictions. So yes, it's continuous and it's a smooth curve. We know what the cube root looks like, hopefully, and differentiable on all real numbers. And last but not least, what about this one? This is an absolute value. Absolute value is continuous, but absolute value makes a v. Okay, it makes a v, and where is this going to be 0? Well, it's 0 when x is -4. At -4 will be the point of this v. That falls in here. So the answer here is no, it's not dot, I can't spell here, not differentiable on -5, or at, let's say this. Let's say at x equals -4. Okay? So that means for these middle two, we can use the mean value theorem. So let's go ahead and find the value there that is guaranteed. And so what that means is we need to find the average rate of change, delta y over delta x. Okay? And that is f of 4 minus f of 2 over 4 minus 2. Okay? And so f of 4 would be 1/3 minus f of 2 would be 1 over 1, and all over 4 minus 2, which is 2. So this is 1/3 minus 1. Well, 1/3 minus 1 is -2/3 divided by 2. So let's clean this up, maybe times a half there, and this is -1/3. So we want to find out when the derivative, we want to set f prime of x equal to -1/3. Well, what is f prime of x? Well, f of x is x minus 1 to the -1. So chain rule gives us derivative of the inside is 1, derivative of the outside is -1 times x minus 1. And that's going to be to the -2 power, okay, which is -1 over x minus 1 squared. Okay, we want to set that equal -1 over x minus 1 squared equal to -1/3. Okay, and oh, look at that. The bottoms have to be equal, so x minus 1 squared equals 3, so we square root. And we get x minus 1 equals the square root of 3. And if we add 1, we get x equals the square root of 3 plus 1, which is about 1.7 plus 1, which is about 2.7. Okay, so the value we're looking for here that makes this true is c equals the square root of 3 plus 1. And that answers the second question.